meaning. And the question is why, if we want to compare group actions, we do it through length functions. So if we want to compare through length functions, this means that actually the length function encodes a lot of the information, which is true in most, I mean, it's conjecturally true in any case where there's some good enough geometry setting, but at least in dimension 2, it's true. And this means that if we are in the setting as above, so we have a manifold, in this case, a closed surface, and we have two negatively curved metrics. That means that on the universal cover, I get two different metrics. And in principle, we have an action on the same space, but with different metrics. So we get two length functions. And these two length functions being the same is actually equivalent to the two metrics being isometric. Isometric, actually something stronger, isometric via an isotope. So actually, the moral is that the Mark length spectrum, Mark length spectrum usually also a way to denote this length function in this setting, remembers the whole geometry, remembers the whole isometric class of the metric. So it's much richer than just asking for QI information, for example. It's actually a specific notion. But this is in the Riemannian setting. Oh, well, and this is conjectured to be true in higher dimensions too. There are some problems of why this is not true, but it's expected to be true. But once we're outside the Riemannian setting, we have in general geometric actions from just metric spaces. Usually we want the spaces to be geodesic, but that's the assumption, like Kelly graphs, for example. And if we assume that the group is hyperbolic, then we have almost Mark length spectrum related. So we have a coarse version. And this means what? So if the two actions have the same length function, then the actions don't have to be isometric, but they are almost isometric. So here this means that there's a map from one of the spaces to the other, which is equivariant. It doesn't have to be continuous. So this is a coarse setting, so we don't care about continuity, but it's equivariant. And it's an isometry up to a bounded amount. So that means if I have 2 points in the space X, we'll look at the image in X star, and the distance of these two images differ by a bounded additive error with respect to the distance in X. So it's still a very good notion under coarse negative curvature. So at least the moral is that the Mark length spectrum, or the length function, remembers most of the intrinsic geometry of the action, which is good. And that is fits into the setting of we're working today because we're restricting to hyperbolic groups. But this is one part of the story. So I should also tell you what cubulations are. So what are cat zero cube complexes? So this is a crash course in 1 minute about what cubulations is. So you should think of cubulations today as combinatorial objects that are built by gluing cubes of unit length. In principle, all these cubes of arbitrary dimension, they have geometry, and we glue isometrically along subfaces. And there's some notion of non-positive curvature going on, which is local, which can only be, which needs to be verified at each vertex, because intrinsically each cube has non-positive curvature because it has a Euclidean curvature. And for it to be cat zero, we also need the space to be contractible, which is the same in this case as the space being simply connected. So in principle, there is a length function, sorry, a length distance here, which actually we can verify is cat zero. But for today, we will be interested in the combinatorial metric coming from the one skeleton. So now we say that each length has length 1, and we're interested in measuring distance between vertices of this cube complex by going through the one skeleton. So what examples to have in mind here? So, well, cat zero cube complexes are defined to be higher dimensional generalizations of trees. Those imperial trees are examples. But today we won't see trees because we are interested in fundamental groups of closed hyperbolic manifolds acting on them geometrically. So the picture on the right should be more suggestive. So on the right, we have not a cat zero cube complex, but a locally cat zero cube complex. It satisfies this non-positive curvature condition on each vertex and is homomorphic to a surface. So since this, so actually what's going on is I try to draw the surface as just gluing a bunch of squares. And it satisfies this non-positive curvature condition. That means the fundamental group of the surface acts on the universal cover, which is cat0. So in this way, we can see at least as surface groups act geometrically on cat0 cube complexes. There's some power machinery that tells us that actually all the manifolds in the setting, the fundamental groups act on cat0 cube complexes. That means fundamental groups of closed hyperbolic free manifolds and fundamental groups of closed hyperbolic manifolds, which are arithmetic of simplest type. Yes, but if you want to remember a picture of a cat0 or locally cat0 cube complex, it's the surface on the right, please. Well, in this case, what is the meaning of the length function? Well, the length function records the minimal length of combinatorial geodesics. It's just what happens in the Riemannian setting, but in this combinatorial setting, we still are recording combinatorial paths of minimal lengths. So in this case, the path is not unique as in the Riemannian case. So for example, here the curve representing the element G, you can translate to the right and it's fine. It represents the same element, but the length is well defined. So we are okay. And also in the setting of actions on cat0 cube complexes, there's a version of Mark length spectrum which is pretty nice. It was due to Meridian Fioravanti. And what happens here is that if you have a group acting geometrically on two cat0 cube complexes, that must satisfy some irreducibility condition, which is not relevant to us today. It's necessary. And if the group is hyperbolic, then actually the length function remembers the whole action, the whole cube complex. So it's not that in the case of general actions of a hyperbolic group in which we remember things up to a bounded error, he will remember everything. So there's an isometry of the two cube complexes, which is equivariant. So actually, in some sense, cat0 cube complexes are much better behaved with respect to the length function. So I hope so far that I've introduced all the objects. Well, assuming we are somehow familiar with hyperbolic space. And now what is the theorem? So I told you that we wanted to compare length functions, but what is the meaning of comparing length functions, right? So the theorem is we have two options. So we have one action that we like to compare to cubulations, which is the action on Hn, which is unique in case when n is at least 3. If n is 2, then you pick any action you like. Any point in Teichmüller space works. And what is the theorem is that for this highly non-combinatorial action, very Riemannian, you can find a sequence of actions on cat0 cube complexes such that the length function can approximate the length function on Hn. By this, we mean this. So this means that essentially, since the quotient this lambda 1m, this lambda 2m, the quotient tends to 1, it's roughly saying that up to normalizing that the spaces Xm, they tend to be more and more homothetic to space Hn from the point of view of the length function, not from the point of view of the space. So actually, what happens from as a consequence of the Hn being highly non-combinatorial is that the dimension of the cube complexes tends to infinity. But from the point of view of the length function, actually you have a uniform approximation of the length function of Hn from length functions coming from cat0 cube complexes. This is the whole statement. So in particular, since we cannot, since the length function of a cat0 cube complex is never the length function on Hn, this sequence must be infinite. So at least this gives some insight that saying there are lots of cubulations. At least there are enough cubulations that we can approximate the action on Hn. Yes, and again, this is for this very particular closed hyperbolic free manifolds because essentially these are the ones we know act on cat0 cube complexes. Yeah, for all these three, we have a lot of cubulation. Yes. Any questions about the statement? Okay, so if not now, well, first I'll give you some applications or motivations to work into this problem, and then I'll give you some insights about the tools to do this. So first, why should we care about approximating actions by cubulations? is because sometimes there are tools that are available in the world of cubulations that are not available or not easily available outside the setting. So one example is cubulation of random quotients. So actually this work was motivated by the work of Futer and Wise. They were studying random quotients of cubulated hyperbolic groups with the hope that most of them are also cubulated hyperbolic. And here lots of them requires a model of randomness that, well, usually a standard one is a density model. But in this case, as opposed to the case of quotients of free groups, which are random groups, here, when we need the notion of random, we also need a well notion of counting in the group. And counting in the group requires an action. So in this case, they prove results about random quotients of cubulated groups, but acting on the cubulation. Of course, that's nice, but in general, if you have a group, the natural action is not the action on a cube complex, it's the action on Hn, for example, if you have a pi 1 of a closed hyperbolic manifold. So actually, you like to do the counting with respect to the action on Hn. So this cubulation result can be seen, well, this approximation result can be seen as a way to promote the counting we know for cubulations to counting to Hn. So in this setting, actually, the right number is, well, the contribution is to add this 1/41 because they could prove density, but actually for very slow density. So actually from this result, we can improve the density to 1/41, which probably is not optimal, but it's much better. This is one way to prove results. And the other way is related to the no growth gap of subgroups. So this means what? This means being able to find subgroups which are of infinite index and quasi-convex, but they are somehow large in a statistical sense. Statistical sense in this case means we look at this exponential growth rate. That means I want to count the number of elements of H in a Borel radius T. I let this number grow to infinity. And in the case of the groups we are interested in now, if we consider the whole group, these balls grow like exponential to the n-1. So now this should be for n. No, it's fine, it's fine. So this actually is exponential, -1 is exponential growth rate of the whole group. And then if you have a subgroup quasi-convex of infinite index, there's a gap all the time. So it's always less than the exponential growth of the whole group. And this theorem is saying that actually you can find a sequence of larger and larger quasi-convex subgroups, such that statistically they see longer proportions of the group. And this was proven by Wise in the setting of actions by cubulations. So in the way to define the exponential growth rate, we need the action, this distance, to be computed from point of view of the cubulation. But now we're counting with respect to Hn, the action on Hn, and this is because we can approximate. This is true for each cubulation, and since we are converging, we can check that this exponential growth rate is a continuous function. So we can promote this result from cubulations again to the action on Hn. And just as an aside, that the way I studied the theorem with Nic is about approximated actions on hyperbolic spaces, but actually we can approximate more actions by cubulations. So for example, in the case of surfaces, we don't need the curvature to be constant. And also, we can also extend this to not necessarily Fuchsian actions, also quasi-Fuchsian actions, which is we deform a representation into PSL2C. These representations, you have the length function coming from the action on H3. This length function can also be approximated by cubulations. And also, we have another way to get the length functions, which is now instead of extending to PSL2C, we extend to PSL NR and the form. So we get representations which are Hitchin representations. If we extend to symplectic groups, we get maximal representations, and we get length functions by looking at spectral radii. And from these functions can also be approximated. So actually, there's some flexibility. It's not something just of rank 1, constant curvature. So this is just an aside. But the reason actually why we're interested in this is because there's a sort of program to understand geometric actions of hyperbolic groups. Well, more generally, of geometric actions of groups in general, finally generated groups. But in the hyperbolic case, usually there's more structure, and we can actually compare things. So this is what happens for a surface group. So surface group, actually, we know there are a lot of actions for surface groups. So we have Teichmüller space, we have actions coming from negatively geometrics of maybe constant curvature, we have Chikchin representations, we have quasi-Fuchsian representations, we have Cayley graphs, cubulations. And actually, there's a way to pack all of this into a topological space, which is actually a metric space. Once we have this space, we can start asking, well, what is the connection between these different structures related to surface group? What is the intersection of Teichmüller space or maybe negatively geometrics with quasi-Fuchsian space? We can start asking these questions. And this fits into this because we have the gray bubble that represents all cubulations, and this theorem is saying that inside this bubble we have Teichmüller space, which is T minus 1 gamma in the middle, which is actually a very small portion of it. So I told you we also have quasi-Fuchsian representation, which is this red bubble, and there's more stuff inside cubulations, which is actually nice. And something we don't know is to what extent this gray bubble might be everything. This is a question of Futer and Wise, saying that any geometric action on a hyperbolic group, or well, a surface group in principle, can be approximated by cubulations. Yeah, this is a very tricky statement, but yes, there's a lot to explore. Yeah, so this result fits into this bigger program of understanding different structures on hyperbolic groups. Yeah, so I have just a few minutes. So at least tell you about the two-dimensional case, why the theorem works. So what is the main tool? The main tool is, well, we want to produce cubulations and cubulations that approximate the action on H2. A way to produce cubulations is by Gibbs construction looking at multicurves on the surface. So we start by multicurves on the surface, and now we'd like to put sort of a topology on the space of multicurves so that actually we can converge to an object that represents the action on H2. And the setting for this is geodesic currents. So what are geodesic currents? So geodesic currents are just invariant measures on the space of geodesics in H2. So this is a space where multicurves live somehow and H2 lives. Why? Because multicurves, we can actually lift these multicurves to the universal cover, and we get an invariant discrete measure when for each geodesic we assign mass 1. And by Gibbs construction, each time we have this space of this set of geodesics that is invariant, we get a dual cubulation. This is abstract machinery, but each time we have this, we have a cubulation, which is good. So this means that cubulations are dual to discrete currents. And now why discrete currents are nice? Because actually these discrete currents remember the length function of the dual cubulation via this intersection number, which is a number that takes two geodesic currents and assigns a real number. This extends the geometric intersection number of multicurves. So what happens? So first, well, which I wrote as maybe the fourth part, is that these dual cubulations, the intersection number remembers the length function, which is good. So if we pair the length function associated to the corresponding cubulation to the multicurve, so the simple closed curve associated to an element in the group, we recover the length function. And also, there's a way to remember the action on H2, the hyperbolic plane by geodesic current, and this is called the Liouville current. That means a current that each time we pair this current with a current corresponding to a closed geodesic, we recover its hyperbolic length, which is good. And the approximating now of cubulations to H2 can be translated into approximation of these discrete currents to the Liouville current. Because this is a topological space, a space of measures, so it has a weak star topology, and continuity of the intersection number is key here to make this work. So this is a sketch of how it works in dimension 2. Just one word about what happens in higher dimensions. In higher dimensions, we want to do the same, and we fail. We fail because there's no natural pairing for codimension reasons. So what we like to do is to find something of codimension 1 that we can pair to something of codimension 1 and satisfying similar properties as what we wanted. And in this case, for example, in dimension 3, codimension 1 means we look of quasi-circles in the boundary of the hyperbolic space. We try to do the same. We fail most of the time, so we win continuity, but with almost continuity. And at some point, we have to do some minimal surface computations for this to be true. But the moral is the same. We want to move this into a space of measures in which we can actually compare these two things and then promote convergence in the space of measures to convergence of length functions in the cubulation. So this is the general strategy. And yes, and thank you very much.
Okay, let's thank Eduardo. So does anyone have any questions? You can either unmute yourself and ask them or post them in the chat. Yeah.
Please, may I ask, your application slide where you're approximating by quasi-convex codimension 1 subgroups, does that work in the finite volume case? Like if you
the no growth gap?
Yes, like this no growth gap here.
So it works in, I mean, they are cubulated. So when you compact cubulate, you win in some sense, but there's no way, I think there's no good enough theory of to approximate yet in the co-volume case. And this is, the problem is that you are, when you act on the cube complex, it's geometric. So you're actually QI to the group, but the co-volume option is not anymore. So cubulating to some, I mean, approximated to some extent doesn't make much sense. I believe there are ways to prove this anyway. This result. This might be known. Yeah, I'm not sure, but I presume it might be known, at least in some cases.
Thank you.
Okay, any other questions? I have one. Do you know, does this work for other rank 1 symmetric spaces?
Other rank 1 symmetric spaces.
I guess
actually,
I'm not sure.
So in that case, most of them are not cubulated. I mean, SON1 is the only case that can be actually cubulated. Okay. So SON1 cannot be cubulated because, okay, the secret of cubulates to have condimension 1 subgroups. And in the complex hyperbolic case, everything, it's either complex codimension 1, that means codimension 2, or totally real. So okay. You don't have ways to cubulate. And in the other cases, you have property T. And property T is an abstraction to cubulate.
Any other questions? Okay, well, if not, let's thank Eduardo again.